Have you ever opened a really heavy door? Like the kind of door you'd find in an old medieval castle, the kind with gigantic hinges and solid wood or metal construction. If you have, you might have noticed it's much harder to get a heavy door to swing than a light door. It's also much harder to get a door to swing by pushing it near the hinge than it is to push it further away from the hinge. A heavy door has more mass, and a large door has more mass away from the hinge. Because of both of these things, we can say that it has a greater moment of inertia. Rotational inertia, otherwise known as moment of inertia, is a number that represents how much mass a rotating object has and how it's distributed. An object with more rotational inertia is harder to accelerate. So how can we measure moment of inertia? There are many ways, but today we're going to look at one particular scenario. We're going to imagine a ball rolling down a hill without friction. Obviously in real life there's always friction, but we're just going to keep things simple. Thanks to conservation of energy, we know that whatever energy the ball started with must be equal to whatever energy it finishes with. The ball at the top of the hill released from rest only has gravitational potential energy, which as we learned in another lesson is equal to mgh. Once you release it, it starts moving, getting faster and faster as it rolls down the hill. But it moves in two ways, translationally and rotationally. The ball as a whole translates down the hill, but the ball also turns, it rolls. So that gravitational potential energy turns into a mixture of translational kinetic energy and rotational kinetic energy. Again, we'll learn the equations for both of these in the lessons. Translational kinetic energy is a half mv squared, and rotational kinetic energy is a half I omega squared. Just as a reminder, m is the mass of the ball, v is the translational velocity of the ball at the bottom of the hill, g is the acceleration due to gravity, which is 9.8 on Earth, h is the height of the hill, and I is the moment of inertia of the ball. So if we can measure everything except for I in this equation, we can figure out the moment of inertia. So we get started and find out that the ball has a mass of 2 kilograms and a radius of 0.1 meters, and the hill has a height of 2 meters, after measuring it multiple times like all good scientists. We then take video of the ball rolling down the hill and use some computer software to calculate its translational and rotational velocities at the bottom. After doing that, let's say it comes out to be a velocity of 6 meters per second and an angular or rotational velocity of 28 radians per second. What is the moment of inertia of the ball? Well, all we have to do is plug numbers into the equation and solve for I. After doing a lot of algebra to make I the subject, we end up with this final equation. We plug in our numbers and solve, and we get a moment of inertia of 0.00816 kilograms meters squared. How good was our experimental value? To figure this out, we'll have to look at what the theory says should be the moment of inertia of a sphere. Assuming it's a solid sphere, a bit of calculus tells us that the moment of inertia of a solid sphere should be equal to 2/5 of the mass multiplied by the radius squared. The mass of our sphere was 2 kilograms, and the radius 0.1 meters, so if we plug those in, we find that the moment of inertia of our solid sphere should have been 0.008. So we were pretty close. It's much harder to get a heavy door to swing than a light door. It's also much harder to get a door to swing by pushing it nearer the hinge than it is by pushing it further away from the hinge. A heavy door has more mass, and a large door has more mass away from the hinge. Because of both these things, we can say that it has a greater moment of inertia. Rotational inertia, otherwise known as moment of inertia, is a number that represents how much mass a rotating object has and how it's distributed. An object with more rotational inertia is harder to accelerate. One way we can measure the moment of inertia of an object is to roll it down a hill. If we can measure the mass and radius of the object, the height of the hill, and the velocity of both rotational and translational at the bottom of the hill, we can use those to figure out the moment of inertia. We do this by writing and solving an energy equation for motion, one that says gravitational potential energy at the top of the hill is equal to the sum of translational and rotational potential energies at the bottom of the hill. Moment of inertia for a uniform object of a standard shape can also be figured out using calculus. You can then use this theoretical value to see just how good your real-world measurements were.